We're outside the Flight Dynamics Research Facility here at NASA Langley. Today is the day they're going to do the ribbon cutting. We're going to go inside here in just a little bit and see all of the things inside of that amazing wind tunnel. So let's break it down a little bit. You can see the building here, that central section right in the middle of the building, that is where the wind tunnel and test section is. The areas around it, that's where the wind is flowing. So we're going to kind of break it down a little bit once we go inside and learn some more.
As far as the tunnel itself, a little bit of the history, you know, the lobby is set up as a little bit like a museum, kind of paying homage to the history that we have here at Langley of flight dynamics work, going way back to the 1920s. Sort of the genesis of these vertical tunnels that Langley has is to research spin modes for aircraft. So the example that I always use is, I'm sure that all of you have seen the original Top Gun movie. You know, Goose does not make it to the end of that movie, and that's because they get caught into a spin mode and that they're not able to get out of, which is a real thing, especially for high-performance aircraft. And so that's kind of what NASA got started. Back in those days, it was NACA, not yet NASA, building the vertical tunnels and looking at those modes and how to recover from those in particular. This tunnel replaces two older tunnels, the vertical spin tunnel and the 12-foot low-speed tunnel. Those came online in 1939 and 1941, respectively. They actually sit over on the east side, so Langley Air Force Base. Those tunnels are being decommissioned, they will be demolished, and that land will be going back to the Air Force Base. So anyway, through the history timeline here, like I said, a lot of research on spin modes, aerodynamics. Over the years, that started to transition to capsules. Since it's a vertical tunnel, one of the things that we do are these free flight test methods, which allows us to adjust the airspeed of the wind tunnel to keep the capsule aloft. I think later on you'll see a demo of that upstairs. And that works well for some of these capsules. So we look at the entry dynamics as a capsule is coming back into the Earth's atmosphere, or if it's going to Venus or Titan, one of Saturn's moons. Basically anything that has an atmosphere, we look at the dynamics that the vehicle has due to that. As we'll move along here real quick, on the monitor you see some of the testing that we've done. This is the Gemini capsule way back in the day, but astronauts do not like to fly like that. So that's the sort of thing that we try to look for, and how can we correct that and get it to fly better. You'll see some of the different test techniques that we have on here too. We tend to be a little bit more dynamic than a lot of the tunnels are. You know, many tunnels are kind of static, where you hold the model in one position, collect data, move to the next one. We tend to do a lot of motion in our test methods. That gives us kind of a unique capability, even aside from being vertical. Then moving on down to the display case here. Here you see a lot of the models that have been tested over the years. These are the size of the models that we do the free flight testing. So you see they started going way back, balsa wood, craftsmanship that goes into those models. Kind of migrated to fiberglass, and these days we do a lot of 3D printed plastics. And then behind you, there's a model of the wind tunnel itself, kind of a dollhouse, and you can kind of see it's this dual return flow path where there's 4 fans that sit on the ground level, direct the air inward, and then it just kind of circulates. And then the test section is upstairs, which we'll go to next. So I'll pass it on after all those words. Ryan, anything that I missed you want to talk about?
Yeah, so just, I guess, a little more about the building itself. So as Corey said, right, it's a dual return, 4 fans. Each fan is 14 feet in diameter, powered by a 750 horsepower motor, driven by a variable frequency drive. We have 2 fans that are actually directly behind us on the opposite side, right on that. Airflow towards the center. Turning vanes then bring it upwards. Passes through a honeycomb and 2 sets of flow screens that kind of homogenize and straighten the airflow before going through the contraction cone where the airflow speeds up. And then we get up to the test section where we have a couple test rigs that were brought over from the legacy tunnels. That's the rotary balance system and the C-strut. When we go up to the control room, you'll see models on those test rigs that we'll point out when we get up there. Downstream of the test section, you have the high-speed diffusers that kind of change the geometry of the cross-section, make it a rectangular shape. Then we go to the top center, where there's a set of turning vanes that then start your return of the airflow out and then down and back to the fans.
4, 3, 2, 1. Cut!
I'm Jeff Edmondson, Wavy TV 10. This is a question for Jared or Dr. Dial. We saw that the Da Vinci spacecraft over there for EDL, this is going to be a really important apparatus for testing, but we also have the X-59 and other aircraft. So how is this going to be important for the aeronautics here at NASA?
Yeah, well, I mean, I guess generally say you just highlighted two of the most important programs that are under development right now. X-59, which has obviously evolved from the point where we did a lot of the testing in a wind tunnel to actual application in flight, which is it's flying almost every day. It was flying again yesterday, and is progressing through its quiet supersonic envelope expansion phase right now. And then Da Vinci is in development. Right, and this is the perfect opportunity. If we are going to make designs, let's design changes. Let's learn it here in environments such as the Flight Dynamic Research Facility before we start cutting hardware and really going into the type of investments necessary to undertake a mission to Venus, which is what Da Vinci is designed for. And those are just two examples, right? I mean, it's kind of exciting to think about what kind of programs will inevitably make their way through facilities like this in the near future. Dr. Dial, anything to add?
It's a great question, Jeff. The administrator has challenged us to move at an accelerated pace at developing the next generation of aircraft and spacecraft. Testing facilities like this allows us to accelerate that pace before we even get into a full development cycle. And so when you talk about reducing risk, saving cost, being good stewards of taxpayer dollars, facilities like this enable us to accelerate the pace in which we discover.
Right away when you get off of the elevator, you see these fan blades. These are actually the fan blades that came out of the 12-foot low-speed tunnel, which was one of the tunnels that this replaces. Kind of have a nice little on display of the actual fan blades. Those date back, I think, to the early 1940s. The original fan blades from that, made out of Sitka spruce, that is a particularly good wood for wind tunnel fan blades. So we'll just kind of keep going on here, and I'll point out some of this. So, Da Vinci is one of the first tests that we're going to run here at FDRF. It's a probe that's going to go to Venus. We tested it in the old wind tunnels, both the vertical spin tunnel and the 12-foot tunnel. They're coming back and going to do some more testing in FDRF here. Hayden Dean works on the project. She kind of leads up some of that testing, so feel free to come back to talk to her and ask questions, but for the time being, we're going to go on around. As you can see, like with Da Vinci, it mounts on the model outside of the tunnel, and then the whole rig moves inside the tunnel for testing. This is the model launch window. So this door opens up when we're going to do a free flight test, which again, when the administrator gets here, you'll see a demonstration of that. This window's open, and that's when the tunnel comes up to speed, then it's where the tunnel gets put in. Like I said, you'll see that in a little bit.
This wind tunnel's opening today. This is awesome. This whole facility is opening today. It's been a long project to get it built, to get everything tweaked and set just right. So how excited is everyone here at NASA today?
Oh, we're very excited. We got a lot of people coming today to celebrate that, and going to have a lot of people coming through here, giving tours, showing it off a little bit. So yeah, we're extremely excited to get it open and start doing some testing.
What is the test area? Give me a description, because the shape of the building from the outside isn't a horizontal wind tunnel, it's a vertical wind tunnel. So give me a size of this.
So that is our unique characteristic, most unique characteristic, is that we are a vertical tunnel. So it's a dual return path, right? So we have fans that sit on the ground floor that blow air inward, and they just kind of circulate. And the test section is a vertical test section right behind us here. It's a 20-foot diameter, 12-sided 20-foot diameter test section that's about 24 feet high is our primary test area.
Okay, got it. And what kind of things are we going to be testing in here? Short term and longer term?
So we test all class of vehicle in here. Actually, the first test that we have lined up is the subsonic flight demonstrator, which is a truss brace wing configuration that NASA's looking at for better fuel efficiency, better efficiency design. The next test that we have set is the Da Vinci, which is a Venus probe. So that's an interplanetary probe that's going to go to Venus and descend into the Venus atmosphere and take measurements of the atmosphere along the way. And then we also have Raven Swift, which is advanced air mobility, kind of one of those newer crazy configurations, looking like an air taxi, very complex configuration.
Yeah, I've seen some of those images before of that. The one thing about this is that, so it's a vertical tunnel. If we're going to test an aircraft, we can put it on an arm, but if it can also do free flight as well.
Correct. Yeah, we do both of those. So we do captive tests where we have an internal balance that are measuring the aerodynamic loads on the vehicle. But yeah, you're right. We also do free flight testing. Since we're a vertical tunnel, again, kind of akin to like a free flight tunnel or an indoor skydiving tunnel, where we do free flights on vehicles, and we can measure the motion of the vehicles as they're freely floating in the airflow.
So how do we measure these vehicles? I see that there's a camera behind you. So is it a camera-based system, or are there other technologies that we use to really study and get that data?
When we do the free flight, it is primarily camera-based, and yeah, we have sort of the standard visual cameras, but we also have motion caption cameras where we have targets on the vehicles, and they track the very precise position and motion of the vehicles. Actually, the same sort of technology that Hollywood uses when they're doing some of their motion capture things.
And I feel that it's pretty comfortable in here. This is an ambient air chamber, so we're not going to pressurize this like the tunnel on the other side of the facility and the center. This one uses ambient air. So give me kind of an understanding of what that is and what that means for tests.
So yeah, you are correct. It's essentially just the outside air that we use here. Regular sea level pressure here same as Hampton, Virginia. Air density all the same. That just gets kind of fed into the fans and circulates, and that's the density, the pressure that we test at.
Earlier in this on this floor, you showed us about the old fan blades that were here. Tell us about that, because I wasn't sure I could hear you clearly. So tell me about those old fan blades.
So those come from, the fan blades on the wall over there come from the old 12-foot tunnel that this FDRF is replacing. That tunnel came online in 1939. It was originally a free flight tunnel as well, but it wasn't vertical. It could pivot to different angles. Those blades in particular are from, I think, the early 1940s at least. They're made of Sitka spruce, which is a particularly good wood for fan blades. They're relatively lightweight. They have good mass properties and thermal properties, which you kind of have to look at for when you're constructing your wind tunnel.
Having this test section be that dimensions that you gave me, what advantages do we have with this one compared to the older tunnels that used to be used here on Center?
So this test section is the same size as what the vertical spin tunnel was. It's bigger than what the 12-foot tunnel was. This tunnel replaces both of those. But the airspeed that we have here is greater than both of those tunnels. This is about twice as fast as what those old tunnels can do. So the performance is better, the air quality is better, we do better conditioning, so that translates to better airflow in the test section than we had at those old tunnels.
How fast are we talking for the wind speed?
About 117 miles an hour is the top speed.
And precision, I would assume, from 0 all the way to 117.
Yes, all the way from 0 to 117. And that can be controlled here. When we do free flight testing, we have a pilot that flies the wind tunnel, that runs it from this joystick right here, that adjusts the airspeed to keep the model kind of in the test section where we want it to be.
Where you want it to be. How many fans are powering to get that wind speed?
We have 4 fans that sit down at the ground level. Those fan blades are made out of carbon fiber, nice and lightweight, so that you can change speed very quickly. But each of those is 750 horsepower.
Oh, wow. So, okay, we still got 4 of those things powering this.
Yes.
Does it get pretty loud?
No, actually, it's much quieter than our old tunnels. You'll probably see a demonstration here in a little bit, so you'll see, but it's pretty quiet, actually.
Okay. Anything else we need to know about this wind tunnel?
Just that, the investment in this sort of infrastructure is what keeps us on the forefront of the technology, and so it's great that we're able to do this, and hopefully we get to do more of it in the future.
Great. Thank you very much. Can't wait to see the demo.
Absolutely.
Awesome. All right, so we're going to be talking about Da Vinci today, the Da Vinci spacecraft that's going to Venus. And we're going to be testing it inside of this tunnel once we get everything kind of up and running. It's going to be one of the test subjects. Tell me about that test.
Yeah, so we're in the stages of planning this test. We're already on the schedule to be like, hey, we got to sneak in between some plane projects to get this test done. But the goal of this test is to learn some more about the aerodynamic properties of this capsule. We are in some of the early design stages of this mission, so we have to do design trades of, how big do the drag plates need to be, or those tiny little wings that you stick off the capsule.
Yes. Right there, yeah.
Or, these colorful spin vanes. What angle do those need to be at so the vehicle actually spins at the rate that the camera that's supposed to be on the bottom of the actual flight vehicle can actually take images of the capsule going down to the surface.
Sure.
So we need to go back into the facility. We already have some data with the legacy facilities like the vertical spin tunnel and the 12-foot low-speed tunnel, but after looking at all that data, we need more. So we want to go back into FDRF and actually get more of that data so we can ensure that our models are correctly, to ensure that we're going to have a successful mission to Venus when we eventually go there.
This is a multi-center event, so we're testing the flight dynamics here in the wind tunnel, but the actual engineering, that's going to be more from Goddard, is that correct?
Yes, it takes a village to send something to another planet. So yeah, here at NASA Langley, we're doing the entry, descent, and landing simulations.
Which is hugely important, especially on Venus.
Well, especially in a case where we can't just test the end-to-end mission. Like if you're going to go fly a plane, you can go, let's go test flight. You can't test flight going to Venus. You have to model it. So we do flight simulations of it from orbit going all the way down to landing with all those different models and components together. And they do a bunch of statistical analysis on it and basically say, hey, within these parameters, we will meet our mission objectives. We will meet those requirements. And so testing in FDRF is just one small piece of that puzzle to make sure that flight sim is behaving the way we need it to meet mission objectives. And then that they can actually build the flight vehicle and execute the mission the way it was designed.
We learned earlier that this is our atmospheric chamber. So our fresh air, our air pressure, obviously Venus, the air pressure gets pretty intense down at the surface. As you go higher up, it would be lower. So are we testing a specific spot in the atmosphere for the flight of this?
Yes.
Okay.
So with the descent sphere, we're focused on the deep atmosphere of Venus, hence the name of Da Vinci. Da Vinci stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging.
Probably should have done that first, but we got it now.
Should have started there.
We got it now.
But yes, so the lower atmosphere, we just don't have a lot of data on, so that's where the planetary scientists want to go. And when you get into that low atmosphere, It's been described to me as soupy. It's very thick. So
Yes.
this descent sphere actually goes very slowly through that soup.
Do we even need a parachute at that point?
No, it's going to free fly for about 30 minutes of the end of the trajectory. Yeah, and it's perfectly on, like usually use a parachute to slow the vehicle down. And this will be on parachute for about 30 minutes before that point, but then it will free float to the bottom. And yeah, so facilities that are low speed like FDRF are perfect for our kind of mission because we're going slow enough where we hit the similar speeds that we would be on Venus, so we can directly compare those conditions. Yes, it's not the Venus atmosphere, but we can make a lot of similarities.
So I haven't done a lot of research on this mission, so correct me if I'm wrong, but we're gonna obviously be around in orbit around Venus or outside of the atmosphere. We'll come in, heat shield, slow us down initially, get rid of the heat shield, parachutes for a little bit.
Yes.
Get rid of the parachutes and then slow down in that soup.
Yes.
That's how it works.
This will all
Very
be
rough.
This will all be encased in an entry vehicle.
Yeah.
So to protect it during
Right, the
those
fins are delicate.
during those first initial entry phases, because it will still get a little hot and it will still have to slow down. So we have that heat shield, but yes, then basically it'll jettison the heat shield and pull the probe out of the back. There is a back cap to keep it all protected, but that gets pulled away. Then the vehicle gets pulled out, and then it'll be on main chute for a little bit. To do some science experiments, and then that parachute line will get cut, and then it will free fall for through the atmosphere and do even more science.
Yeah, the surface of Venus is pretty hot.
Yes.
So that's a whole nother conversation. We're not worried about that in here because we're learning
No.
about the flight dynamics. What scale size is this compared to the actual vehicle?
This is a 75% scale model. And we're in the early design stages, so that has actually scaled up. So in reality, this is probably looking more like a 66% scale model.
Cool.
The real flight vehicle is about 1 meter wide, so I think about that large
Great.
in diameter.
Thank you very much for the information.